Boy. So this is a Times DSP 1600 4 ohms, and the reason it's called DSP 4 ohms is because we've got these little chips here. So we've got a PCM that's going to be dealing with the audio input, and then this chip here is going to be kind of converting it into pulses. It can take an audio input signal and change it into digital PWM output ready for drivers and stuff. But this chip is dealing with all the low pass and stuff. But anyway, that's not really what I'm looking at here. I repaired this amplifier. It had a dead output section. One of the halves of the full bridge died, so repaired that. It just needed FETs. Didn't even need a driver. So that was pretty sweet. So I powered it up after the repair, and obviously probing the low side drain of both sides of these. Checking this on the scope, we have something that looks like this. I was like, that's not looking so great. Let's zoom out a little bit. Zoom in on the time divide just to show you that again. So we've got just a tiny little pulse, and I was like, hey, that's not right. Okay, what's going on here? This is not something I'm used to seeing. So this is what we have on the low side drain. High side, obviously we've got rail. Low side drain, we have these tiny little pulses like this, and I was like, oh fucking hell, something's not right, is it? So I was like, okay, what happens if I apply an audio signal? So I'm going to apply an audio signal and check what we have on the speaker terminals. Let's grab my RCA here. So now with an audio signal, I was hoping that this would come back to life a bit more what I'm used to seeing, with a nice square wave on low side drive, low side gate, low side drain, sorry. And no, we actually have the audio kind of modulated there, but it doesn't look like it self oscillates. It just kind of like, it's got the audio PWM, the changing in dead time and stuff, the changing in duty cycle there. You can see that's what it's meant to do. We've got 46 Hertz going in. So if I probe the output speaker terminal now, let's zoom out on the time divide, go back to reject high frequency, we're only getting the top half of the sine wave. I wonder if I can get that to stick on the scope screen. There we go. So we're only getting the top half of the sine wave, and that's on both of these. So this is a full bridge amplifier, and on both of the speaker terminals we're only getting the top half of the sine wave. I was like, fuck, there's something wrong here, something not going right. Need to try and figure out what the issue is here. It should have obviously both parts of the sine wave there. So I traced this all back. I was a bit confused because this side of the full bridge survived. So I was like, right, if this was an issue with the drive circuit, then this side should be trying to do the full sine wave, and this side should be the one with the issue, because this half of the full bridge didn't have any issues. So I was like, fuck. So I traced the issue, and the issue actually comes all the way back down to the output of this kind of audio chip here. And I was like, oh right, maybe something spiked back down to this audio chip when it blew, and it's damaged part of the circuit in here. So I replaced this chip. Didn't make any difference. And then I looked a bit further down, and I noticed that actually this kind of half sine wave thing was actually coming out of this chip as well before it went into this one. So I changed this one. No difference. What the hell is going on? Literally, you can probe the output of this PCM chip here, and we can clearly see that little half sine wave thing is coming from this chip. There we go. That's the PWM for the half sine. You can see the gaps in between that kind of like thick bit of noise there. That's the gap. That's the 0 volts. And if I go to the other side of this resistor, you can see there, that's the signal. That's the signal being sent to the drive circuit. So the drive circuit is doing its job. It's coming from in here. So I was like pulling my freaking hair out, not that I have any, trying to figure out what the hell was going on with the preamp circuit. I was thinking something's wrong with the preamp circuit. But just out of interest, I decided to see what would happen if I connected a speaker to it, to have a listen to see what horrendous noises it would create when connected up to a speaker. But weirdly enough, I found that it works. Like, it sounds perfect. This speaker is going in and out perfectly. It's not, you know, just shoving out. It's not just pushing out or just pulling in. It's moving in and out perfectly. Which, I was like, what the fuck? So, this amp is working fine. This is just how this fucking thing works. It only produces the top half of the sine wave on both of these. And that's how it creates the audio wave. So one of these is pushing the cone up and then it goes dead, and while the other one pushes the cone, but because it's wired backwards to the one that's pushing, it pulls it in. So it's going, so this one's like push the cone up, and this one's like pull the cone down, push the cone up, pull the cone down. Like, what? I have never seen a full bridge do this. What the fuck? Why would you do this? It actually sounds pretty clean, like it's doing a good job of it. There's not any audible crossover between the two. And if I just remove this right now and turn the gain up a little higher, I'll show you what it looks like on the scope screen with both of these probes hooked up, so we can see. Yo, so here she is. Replaced these bars with these solid DD cables. They won't vibrate out again, and they actually have a slightly lower resistance than these bars, so that's a positive. All 8 of these output MOSFETs have been replaced with 61N20Ds, which are much higher current, lower RDS MOSFET, which is going to be running cooler, a bit better, more reliable operation. Now, these chips, one of them was really bad. Just to give an example what I replaced, here's an example chip that's similar. Had to replace the main drive IC chip, had to replace the high-low side PWM conversion chip. On the back, there was a couple of resistors. This one doesn't have anything on the back, but on the back there's a couple of resistors I had to replace at the top just here, 10R resistors, and there was also a couple of traces that I had to rerun because of that massively exploded area. You can see there I've had to actually solder to leg 3 to go around the back, which is for VS high side source. So yeah, that was a bit of a mission. The bootstrap diode, I had to replace that one at the top there as well, just up here. I think that was it for this driver card. In the preamp section, had to replace this optocoupler and these 2 capacitors here. Very strange that they died at the same time. They're kind of not part of the same circuit, but very strange. You can see them here. That got that back up and running. Also had to replace one of these diodes here across the gate resistor, as that had gone short and that wasn't providing decent blockage on the way into the gate, so I had to replace that as well. And as you can see now, when we give it 12 volts to start with. You can see she is very happy.
And put some stank on it!
These Alpines are an absolute mission to work on. They're incredibly complicated, and when they fail, loads and loads of stuff goes down, tiny little components. So this one I've had on the back burner for probably 3 or 4 years now. It's one of the first amplifiers that I picked up. I think someone gifted it to me to try and see if I could get it back up and running again. I took one look at it and I was like, what the hell is this? So I actually was about to nick the terminals from it. I pulled it out from my donor pile and I was about to steal the terminals, but I looked at it and I was like, I don't recall working on this really, so let me have another look at it now to see if I can fix it, and if I can't, then I'll take the terminals off it, but otherwise I'll leave them on. So the first thing is it wouldn't turn on, and that was down to this transistor here, which is part of the remote turn-on circuit. This was failed and shorted, so I had to replace this transistor first to even get the thing come on, so that took a little bit of time to find that issue. And then if we go up to the screen here, now with the output section, the MOSFETs had failed, and naturally that had taken out the drive ICs, which are 2010S here and here. Got 2 of these. This is actually a full bridge amplifier. Then it had also taken out all 3 of these chips. Now these are kind of, how to explain, they apply the PWM drive wave to low side rail, and they split it so that the PWM rides along low side rail ready for the input of low side for the drive ICs. Now yeah, one of these had failed really badly, so I just replaced all 3 of those. Then I found that one of these transistors, which is a 5401 2N5401, that had shorted, and so I wasn't actually getting any drive to this or the inputs of the drive ICs because I had one of these that was shorted, so I then replaced that. And then I still wasn't getting any drive input to the drive ICs, and this was a big head scratcher. I went around the whole board for ages. I found some more stuff on the bottom of the board. Over here, there was some resistors over this side that were completely failed. Let's have a look. Where are we? Here. So yeah, this was a bunch of 6.8 ohms in parallel with each other. So I just replaced it with a larger 2.2 ohm, and that works absolutely fine. Other stuff on the board, there was some resistors over here that I had to replace. Now, the damage that was preventing me from getting drive was all the way over here in this section. So this shorted transistor had actually spiked kind of high voltage over to this circuit. Now, I'm not going to pretend that I know in depth what this circuit exactly does or how it works. I just know that I saw this little chip here with a slightly kind of broken leg, and it looked like, you know, that might have failed there. So I was actually right, this had failed badly. So I replaced this VT, so SP and VT, and then just for good measure, I don't know if they were actually dead, but I replaced this, and this, and also this one here. And then, lo and behold, the amplifier came to life, which is crazy. So many things on this that failed. So on this ground zero, or sound digital as the circuit originally was, had one FET that exploded its leg in the power supply section. Let's remove that. It sent a huge spike down the gate path. The 10R was dead. And that sent the spike all the way down here, and it completely killed the drive IC for the power supply FETs. It's not a 4427, that is incorrect marking, it's something completely different. And then when that died, it also completely killed this 10R resistor that is feeding it with VCC. And I thought that that was probably about it. It's probably just gone to the driver, just gone to the resistor, and then it's all good to go. So replace the resistor, replace the driver, and what I noticed was that when I turned the remote on, the VCC for this chip, which is supposed to be battery voltage, it's supposed to be like stuck at 12 volts, was going down to ground. So with the amplifier off and the power into the amplifier, I was getting 12 volts at the VCC, but then as soon as I applied the remote, it sunk down to like 2 volts. I was like, wow, okay, what's going on here? And I confirmed, I did have a schematic on hand, which was useful, and I confirmed that that's supposed to be tied to battery voltage, and it's not supposed to move around. It's supposed to literally be battery voltage at that terminal there, VCC. So it turns out that probably somewhere on the board, there's a blown trace that is meant to connect this side of the 10R, this side of the 10 ohm resistor, which is for this drive IC, to the battery voltage. There's battery voltages over here, but there's probably going to be a blown trace somewhere, maybe on the underside of the board. So by bridging battery voltage input, which is over here, there's a nice handy version over here, and then taking it round and forcing it into the chip here, the amplifier comes on and performs perfectly fine. So yeah, really strange fault, and still can't see where the blown trace is. It'll be so small. It could be inside the layers. This could be like a triple layer PCB or something. But yeah, that works absolutely fine. So what I'll do is I'll tidy this up and make a shorter run, either from here or I'll find somewhere else at battery voltage. I think battery voltage also comes from over here near where the PRC is, because it registers battery voltage. And yeah, then that will be good to go. Okay, gentlemen, MA6K, common fault. The amplifier keeps going into protection randomly at random times after being powered up. Can be running idle, can be running a load. It just keeps going into protection, and we don't know why. Common issue. After replacing a bunch of things on the output driver card, can't seem to find the fault. However, watch this. I have the oscilloscope probe latched onto the protection output pin from the output driver card. This is the last pin here. As you can see on the scope here, there is some DC offset on that pin. This is the problem. When DC appears on this pin, it sends the amplifier into protection mode over here at the power supply driver board. So there shouldn't be any DC here, and this is slowly rising, and once it gets to a certain point, the amplifier will click into protection mode. However, watch what happens when I blow some cool air on this section of the output driver. Look at that! All of a sudden the DC has disappeared, as if by magic. So we already know that these output drive transistors run very, very hot. These are running at like 60 degrees Celsius. Whew. That was close. These are running at like 60 degrees Celsius, which is not ideal. I don't seem to see drivers running that hot usually on this type of output section, so something is not quite right with how this has been designed. They're either the wrong parts, or they're under too much load, or something is not quite right. There's some more voltage there. Let's get rid of that. There we go. So I'm just going to take my thermal imaging camera. We're going to have a look at how hot some of this stuff in the output drive circuit is running. Okay, as we can see here, we have a hotspot of about 82 degrees Celsius on these output drive transistors, which is a bit hotter than I just said, 86. Goodness me, this is definitely toasting up a little bit here in the output section. So yeah, that is definitely pretty toasty, and that is actually how all of these amplifiers are. I've tested multiple of these, and even running idle, this stuff just runs really hot. 92 degrees! And look, we have some DC offset here on there again, and we just blow it cool. There we go. And now after blowing it cool, we can see that the temperature hotspot has probably reduced down to, yeah, it's down a little bit. It's down a little bit under 90 again. So yeah, the issue then seems to be heat. So I am wondering whether we need to replace these output drive transistors with some that don't run as hot, or some changes need to be made to the output drive circuit in general, which will prevent this from running so hot. Perhaps different value gate resistors, perhaps different pull down resistors, perhaps changing the switching frequency slightly. Or as a temporary fix, which might actually turn into a permanent fix, we could apply a fan just above this circuit here to keep everything cool. So we can attach a fan to the heatsink here and just have it running off the 12 volt regulator here to feed 12 volts to the fan, so that it's constantly cooling down this circuit, and that will prevent it from going into protection mode. It's not obviously a decent fix, because there is still a problem with the circuit causing that to get so hot in the design. But at the moment, that's the best solution I can find for a quick fix for these. I hope that helps. Let me know if you have any questions. So, the amplifier obviously had dead power supply transistors, as you found out. So I've replaced those now. They're all working fine. However, the problem with the amplifier, and the reason it blew, is this transformer. So 12 volts is supposed to come in here at the 12 volt terminal, goes through the fuses, and then it comes to the transformers on these two middle pins here. So you got these two here has 12 volts on it, and these two here has 12 volts on it from the terminal. Okay, it then goes round the transformer and comes out, and it's meant to be on pin number 2 of these FETs. So it's meant to be on the backs of these. Okay, so we have 12 volts coming in here, and we have 12 volts on this bank, 1 2 3, this bank, 1 2 3, this bank, 1 2 3, because it's beeping. But this one, we have nothing. So 12 volts isn't making its way to these 3 FETs, and that's why it blew. Because these 3 were dead, this whole bank of 6 weren't able to do their job, and so therefore this bank of 6 were under high stress, because it was only these ones that were powering the whole amplifier. So these ones weren't doing anything. So 12 volts is coming in here to this, you see this gold wire here. 12 volts comes in there, it then loops around and goes around the transformer and comes out here. But there's a break in there somewhere. See, these aren't connected to each other. The 2 red ones, beep, they're connected, but the 2 gold ones, they're not connected to each other. Therefore, there's a break in this wire somewhere around this transformer. So I'm going to have to pull this off and see if I can repair it. But if I can't, then these things are not really, you can't get these anymore. I'll have to probably rewind this whole transformer, which will take a long time. You're not going to believe this, but see this here, this little yellowy thing? this is actually the protective silicon that goes onto the transformer legs when they are manufactured, when they're wound by the guys who wind them, and then sent over to, you know, the amplifier factory or whatever to get mounted into the board. So this protective silicon tip hasn't actually been removed from the transformer leg. Therefore, it was not making a decent solder contact into the PCB because obviously it's coated in the silicon protective layer. So just need to take that off, and then this should work like new, or better than new in fact in this case. So the first one we're going to look at is this Solid Audio F2500D. Now this is in fantastic condition considering its age. Usually when I get these in for repair, they're all battered up to pieces, scratched and dinked and stuff, missing parts, and this one's actually looking fantastic. They're pretty old amplifiers now. And likewise inside, this looks great. I don't think this has probably ever been repaired before. This all looks clean, fresh as hell. There's no thermal paste smeared everywhere, as you tend to find in these ones that are repaired all the time. Yeah, the driver cards never come out of here, so this is fresh. Damn, this has lasted a long time. Unfortunately, as you can see, we've got some visible damage down here. The power supply section has blown, which probably means that the output section is dead as well. Now, these are old Class D amplifiers, and by that I mean they use N-channel and P-channel MOSFETs in the output section. So, although this is only like 2.5K at 0.5, or you know, it's about sort of 1800 watts at 1 ohm, this uses a whole load of MOSFETs. And this is like what I was saying in the videos and the stuff that I've done about the full bridge and new amplifiers, is that you can get all this power from just like 2 or 4 MOSFETs now, whereas back in the day you needed like, I don't know, flipping 4, 8, 12, you needed 24 output FETs for that, just basically like 2K. So yeah, but very old amplifier, and we're going to get her back up and running today. So this amplifier actually has 4 separate little amplifiers inside that all combine, they all parallel after the filter section to drive a 1 ohm or 0.5 ohm in this case load. So we've got 1, 2, 3, 4 inductors, and each little quarter has 9640 and 640N MOSFETs. That's P channel and N channel FETs. The reason this amplifier has failed is because one of these little quarters of the amplifier has died. So we have shorted MOSFETs, both 9640 and 640N, on this little fourth of the amplifier. The other ones are all okay. However, given the age of this amplifier, it would make sense to just replace all of them because they might be on their way out in terms of lifespan anyway. When these die, sometimes it can kill the little drive transistors on the driver board over here, so it might be a good idea just to change all these anyway. These little parts are pretty cheap and it doesn't take too long to swap them out, so I might do that as well. Basically, just completely rebuild this amplifier with all the drivers and FETs and gate resistors, etc. And obviously we need to rebuild the power supply because when the output section died, it brought the power supply with it, which tends to happen. So I reckon that it's time just to completely rebuild this amplifier. It's in lovely condition, so let's bring it back to as new as we can. So this one here is an Atomic 7K, old school half-bridge Korean Class D mono amplifier. Now this one failed due to a tiny piece of copper wire strand floating around inside the amplifier, and what it did is it actually shorted out this side of MOSFETs against this trace. Now this trace is responsible for carrying the 12 volts auxiliary rail from these rectifiers of this auxiliary tap on the transformer, little wind here, up to the regulators up here on top of the board, and it actually passes really freaking close next to these MOSFETs. I don't like how close this trace is because you've got high voltage on this high side MOSFETs here, like freaking high voltage, and you've got switching as well, which is noise inducing, and then you've got this trace here carrying the 12 volt auxiliary rail right next to these pads, and I don't like that. But what happened, this amp has been repaired before, and when the MOSFETs are being replaced, what's happened is some of this insulation from the trace was not present by these pads where the soldering iron has kind of rubbed over them in the past multiple times. I think it's probably been repaired a few times. So what happened is when that wire strand was floating around, it unfortunately touched the positive rail and touched a little bit of the trace here that didn't have insulation on it. and shorted out all of this bank of FETs. It completely exploded the drive IC on the driver card. So in order to get this back up and running, I thought it was a good idea just to replace the whole output section all in one go, because it's good practice. When the amp fails like this, it can send spikes to the others even if they read fine. So all output section MOSFETs are being replaced. I've also had to replace some of these gate resistors that were reading a little bit out of tolerance. It probably wouldn't be such a big deal, but they were reading a little bit out of tolerance, so replace these. The ones that are on the board here are tiny bit smaller, but it's not an issue. Gate resistors do not pass any current. I don't even know why they bothered using these great big ones to start with, but yeah, absolutely fine. 33 ohm gate resistors. These are all now reading exactly in tolerance. This original trace that goes along the side here, rather than just kind of take a tap of where it broke, because obviously when this happened, it completely obliterated like a big section of the trace here. So there's a big hole in the trace where it was run. So what I did is I've just pulled it all the way back here, and I pulled it all the way back to these rectifier diodes here, and I'm going to run a jumper trace underneath the board to get this 12 volt auxiliary up to the rectifiers without it having to pass by the FETs unnecessarily again. So that can go in the bin. We need to replace both 12 volt regulators, these KA7812s, because obviously they failed, having been shorted to positive rail, so they go in there. I will need to check out a bunch of these other capacitors and stuff around this section, make sure that nothing else got damaged when it took a hit with the positive rail, but I think we're going to be okay. I have already replaced all 4 drive ICs with the IRS21844S. That's all good to go. So once I have rerun the trace from the auxiliary rail, replaced the 12 volt regulators, then I'll be ready to test the amplifier out to see if there is low side switching on the output section. If I'm happy that the output section comes on and it's going to switch the FETs on and off properly without causing any more damage due to anything else on the board that's bad, then only then will I fit the output FETs. So I always check through before I fit the output FETs, make sure that I'm happy with how the circuit is acting, making sure the drive waves are beautiful and perfect before I fit any output FETs, and we should be good to go on this one. Luckily the power supply section was intact. If that had failed as well, that would have been a freaking expensive repair, but luckily the output section was not damaged. The customer was very sensible actually. When this amplifier failed, he heard a massive pop from this area over here where the FETs exploded and completely obliterated, and he did not power the amplifier back on again after it went into protection after hearing the loud pop. That is a good customer. The best thing is not to try and power the amplifier back up again. If you heard a big pop and it's gone into protection, do not try and power the amplifier back up, because you will kill the power supply section. So yeah, awesome stuff. That should be good to go today. Okay, let's do this. First gear. Gonna clutch up nicely. Nothing coming down the pit lane, obviously. Get these tyres getting stanky. Spicy tyres. Too much spin there, lost a lot of speed. Try and keep it going. Oh, it's freaking, it gets roasty toasty hot in there, like sweating out big time. So this here is a common issue I tend to find in these JBL GTO amplifiers. This is a GTO 7001, and it's common also in the 14001 and probably in the 24001 as well. If these amplifiers are left to sit for a long time without being powered up or connected to a 12 volt supply, these power supply capacitors I don't think are particularly high quality, and the issue that you'll find is after being sat for a long time, these capacitors will become critically empty, and when you try to connect up power back to the power terminals here, the fuses will just continuously blow, and eventually if you keep trying that, these capacitors will explode. As we can see here with this one, I have the 12 volts and ground going in, and I have limited the power supply to 0.6 amps, and what's happening is it is drawing current even though no remote is applied, it's just the 12 volt and ground, and what's happening is these capacitors are drawing current from the supply, and gradually the voltage is rising slowly as I'm letting 0.6 amps into these capacitors. Basically, once these are fully charged and this reaches to 16 volts, which is its limit, the capacitors will no longer draw any current. So I guess it's similar to kind of refurbishing a battery. If a battery has become critically empty, you can kind of get it back to life by slowly charging it over a long period of time, and you know, whatever. So this is a similar thing, but for capacitors. I've never really seen this before, only on these amplifiers. And once, like I say, this voltage does reach up to 16 volts, I will then be able to turn it off and turn it back on again, and there'll be no current draw. It's quite weird. And obviously, whilst current is being synced into these capacitors, they do warm up, so they're probably running at about 45 degrees Celsius at the moment. I could lower the current a little bit here just to allow them to do what they're doing a bit cooler. But yeah, this amplifier I bought off eBay for £35 because it was deemed faulty because it was blowing fuses. This capacitor here is a little rounded on the top. This is the one that's warming up actually quite a lot. This one here, this one's not really warming up. This one's pretty cold. This one's pretty cold. This one's pretty cold. So it's only this one that's getting hot. As this is going to be the one that's drawing the current. So obviously the right thing to do is to replace all of these capacitors, which I will do. However, I just want to power the amplifier up and see if there's any issues elsewhere on the board. I don't think there will be, but I just want to check. So just wanted to show you this really weird thing with the capacitors. As you can see, we're at 9.3 volts now, slowly rising up as the thing is drawing current. Look, so now we've got to 16.3, which is what this bench supply tops out at. And yeah, the capacitors have cooled down. They're cooling down now. Just mostly this one and this one a little bit. And as before, I can go all the way down now to a lower voltage and instantly all the way back up again, and it doesn't draw any current anymore. So that has reconditioned this capacitor for only up to 16.3 volts. If the supply did allow me to go higher, then it would continue to draw current slowly and then taper off like it has. But considering this is going to be in a car only at 14 volts, 14.4 or 15 volts tops, that's absolutely fine for it. Oh, fuck. Fully unfit. No! And if you have the balls, if you have the balance and the balls, with my trusty little bench lamp here holding the board up, you can replace the drive ICs without removing the driver card. Ooh, without removing the driver card. I've done this multiple times. It saves a lot of time. Just get up in there, replace the driver cards on the board while it's still mounted in there. Yeah, definitely worth using some solder flux for that. This shit, man, get some of this shit. It's the best solder flux that money will buy. Honestly, it's actually the best fucking shit. I have tried all of it. Good capacitor, bad capacitor.